So imagine you're standing in a field, right? You're watching someone shoot an arrow into this completely blank, solid wooden fence.
Okay.
Thwack. It sticks right into the middle of the wood. And then they walk up to the fence with a bucket of paint and they carefully, meticulously draw this pristine red bullseye directly around the exact spot where the arrow landed.
Oh, man.
Yeah, and they step back, point to it, and proudly declare to everyone watching, like, look at that, a perfect shot. I mean, I am a master archer.
Well, it's completely absurd. You would never accept that as proof of skill in a million years.
Right.
I mean, you'd laugh them out of the archery range because the entire point of a target is that it has to be there before you draw the bow.
Exactly. That is the fundamental rule of the game. But what if I told you that this exact same sleight of hand happens constantly in the halls of modern science?
Yeah, it really does.
So welcome to today's deep dive. Our mission for you today is to uncover the statistical trickery that produces those sensational, just too good to be true headlines you see popping up on your feed every single week.
We all know the ones.
Right, the ones like eating chocolate every day helps you lose weight, or uh, drinking this specific type of wine makes you live longer.
Yeah, we are exploring a pervasive and frankly deeply problematic phenomenon known in the scientific community as data dredging.
Data dredging.
Right. You might also hear it referred to as data snooping or p-hacking. It's this practice that dramatically inflates the illusion of scientific discovery. And worse, it undermines the very foundation of how we figure out what is actual objective truth and what is just, random noise in a spreadsheet.
So to understand how researchers, even well-meaning ones, right, how they get away with painting the bullseye after the arrow has already landed, we first need to unpack the foundational math they're exploiting.
We have to talk about the significance level.
Yeah.
Uh,
Like, how does a scientist actually prove that they found something real?
well, it all comes down to the conventional test of statistical significance. When a researcher runs an experiment, they are essentially testing the probability that their result could have happened by pure chance.
Right.
They do this by testing their data against what we call the null hypothesis, which is basically the baseline assumption that there is no real relationship between the things you're studying.
Okay, wait, let me make sure I'm visualizing this correctly. So if I am testing a brand new cold medicine, the null hypothesis is simply this medicine is basically a sugar pill.
Yes.
Like, it does absolutely nothing, and if anyone happens to get better, it's just the random chance of their immune system doing its normal job.
That is a perfect translation.
Yeah.
Your goal as a researcher is to gather data that is mathematically strong enough to reject that null hypothesis.
You want to prove the medicine actually did the healing.
Exactly. But science acknowledges a fundamental truth, which is that there's always some risk of a false positive.
Sure.
You might mistakenly reject the null hypothesis when it's actually true just because you got a weird, lucky batch of data.
A fluke.
Right. So this accepted, built-in level of risk is called the significance level. And conventionally, across most scientific disciplines, this is set at 5%.
Ah, the famous 5% threshold. So we essentially accept that we might be wrong 1 out of 20 times.
Yes, and that is exactly where the trap is set. Because if you test enough random hypotheses, the math dictates that 5% of them will erroneously appear to be statistically significant purely by chance.
Oh, wow.
Yeah, if you inject enough randomness into any data set, you're mathematically guaranteed to find some spurious, totally meaningless correlations.
Wait, I really want to pause and emphasize this for you listening. So if I decide to test 100 totally random, entirely unconnected things.
Like whether wearing blue socks on a Tuesday correlates with the stock market going up.
Yeah. Or if, like, eating bananas correlates with winning the lottery. The underlying math virtually guarantees that 5 of those tests will look like groundbreaking scientific discoveries just by pure blind luck.
It does. It literally guarantees it. This is a well-documented statistical phenomenon known as the multiple comparisons problem.
Wow.
And this brings us to the term p-hacking. The p refers to the p-value, which is that mathematical number representing the probability of chance.
Right. And the term p-hacking itself was actually coined in a 2014 paper by 3 researchers behind a blog called Data Colada. They've done incredible, exhaustive work uncovering these exact mathematical problems in social science research.
So the true deception happens when researchers compare dozens or even hundreds of variables, but they just fail to alert the reader to the total number of comparisons they actually ran.
Exactly. They just published the 5 that crossed the finish line, and quietly hide the 95 that completely failed.
That is the essence of data dredging. They run the numbers through a supercomputer until they find that 5% chance anomaly, and they present it in a shiny academic journal as the only test they ever ran.
Yeah, it's a huge problem.
Okay, so knowing that the math guarantees false positives if you run enough tests, how do researchers actually exploit this in practice? I think it's time we open up the data dredger's toolkit and look at the mechanics of this illusion.
It's a surprisingly varied toolkit, actually. The first, and maybe the most common method, is drawing conclusions from the exact same data that you used to form the hypothesis in the first place. Wait, say that again?
So a key tenet in proper statistical analysis is that you must test your hypothesis with fresh evidence. Evidence that wasn't used to construct your initial guess.
Oh, wait, so if I'm using the exact same data to both invent my theory and prove my theory, it's almost like grading my own test, right?
Exactly.
I take the test, look at the answer key, and then boldly declare that I knew all the answers all along.
That is a phenomenal way to frame it. Let's look at a concrete example. Say you flip a coin 5 times. It lands on tails 3 times and heads twice.
Okay.
You look at that small data set and you hypothesize, this specific coin must be weighted. It favors tails 3/5 of the time.
Right.
If you then use that exact same set of 5 flips as the empirical proof to confirm your new hypothesis, the confirmation is completely, utterly meaningless.
Because it's a circular argument. You are literally using the data to predict the data.
Yes.
To do actual science, you'd have to state your guess about the weighted coin and then flip the coin a completely new set of times to see if your prediction holds up in reality.
And surprisingly, highly educated researchers fail to do that new set of flips all the time.
That's wild.
Yeah. So the second tool in the data dredger's kit is what we call optional stopping. Now, this is a valid procedure in some very strict pre-planned contexts, but it is incredibly easy to misuse.
How does it work?
It happens when a researcher continuously collects data, checks the p-value after every single new data point, waits for it to dip below that magic 0.05 threshold, and then immediately halts the experiment.
Oh, I see the game here. It's exactly like a casino gambler playing roulette.
Yes.
They sit at the table, spinning the wheel over and over, going up and down until they happen to be up by $10. They immediately cash out, run home, and then write a best-selling book claiming they have a foolproof mathematical system to beat the house.
That is exactly it.
They didn't beat the house. They just stopped the clock at the exact millisecond they were winning.
The casino analogy is spot on.
Yeah.
And if we look under the hood at the mathematics of why this breaks science, it introduces a crucial concept called counterfactuals.
Counterfactual. Okay.
To properly calculate a valid p-value, honest researchers must mathematically account for what they might have done in reaction to data that could have been collected, but wasn't.
Okay, you're going to have to break down counterfactuals for me because that sounds like we are drifting into, like, a sci-fi multiverse.
It does sound like quantum physics, yeah, but it's pure statistics. Think back to your casino gambler. The standard p-value formula assumes you walked into the casino planning to play exactly 5 hands of roulette no matter what.
Right.
But if your secret unstated plan was actually to play up to 100 hands and stop the second you got ahead, well, the mathematical universe of things that could have happened expands drastically.
Oh, I get it.
Yeah. If you optionally stop, you're ignoring the parallel reality, the counterfactual where you kept playing, and your temporary winning streak plummeted back down to a massive loss.
So by hiding the fact that you would have kept going if you were losing, you break the original math formula. You artificially lower the p-value because the formula thought it was analyzing a fixed, predetermined test.
You've nailed the mechanics of it. Honestly, if the null hypothesis is true, meaning if there's absolutely no real effect, you can reach literally any significance level you want if you are just allowed to keep collecting data indefinitely and stop exactly when you get the number you want.
That is genuinely terrifying.
It is.
But what if the data is already fully collected? Like, you can't optionally stop anymore. What else is in the toolkit?
That brings us to post hoc grouping, which is essentially endlessly slicing and dicing the data after the fact.
Oh, so?
Imagine a massive data set of hospital patients.
Yeah.
A researcher might check if recovery from a certain illness correlates with age. If the math doesn't show significant result, they don't give up. They check if it correlates with sex.
Okay.
If not, maybe it correlates with age after controlling for sex. Or maybe it correlates with age, controlling for sex, but only in patients who live in certain zip codes.
So you just keep shuffling the deck, changing the rules of the game, Until you finally draw four aces.
Cool.
And there's one more tool I noticed in the sources that I just found hilarious. It's forming a hypothesis suggested by completely non-representative data. The August 7th birthday example.
Oh, yeah. This is a classic textbook illustration of how ridiculous data dredging can get.
So imagine you run a random demographic study of 1,000 college students, and just by total fluke, there happen to be exactly 2 people in the entire massive study who were born on August 7th. Let's call them Mary and John.
Right.
The data dredger looks at Mary and John and starts hunting for random similarities between just those 2 isolated people. They test hundreds of potential connections. Finally, they discover that Mary and John are the only 2 people in the entire study who switched their college minors 3 times.
And out comes the hacked hypothesis, packaged as a scientific breakthrough.
Yeah. The researcher proudly publishes a paper concluding, people born on August 7th have a significantly higher chance of switching minors more than twice in college. And if you look at their study out of context, the math seems to bulletproof it. 100% of the August 7th babies in the study switched minors 3 times. It's statistically significant, but it's a completely spurious, meaningless correlation.
And the ultimate test of science is reproducibility. If any other university runs a study to check that August 7th hypothesis, the illusion falls apart instantly.
Yeah.
Mary and John were just a fluke.
Right. Okay, so Mary and John's college major is a funny, harmless example. But what happens when these tricks make it out of the theoretical lab and onto our news feeds?
That's the real problem.
Yeah, when we are talking about public health and media reporting, the things that actually affect your daily life.
The real-world fallout is massive and deeply misleading. Let's look at how the media can be inadvertently or sometimes intentionally weaponized by this. The chocolate weight loss study is the perfect case study.
Oh, I'm so glad this was in our sources. This is John Bohannon's 2015 social experiment.
Yeah.
So he's a journalist who deliberately conducted a fraudulent, manipulated study just to prove to the world how easy data dredging really is. He managed to get his study published in a journal called the Institute of Diet and Health, and it successfully fooled millions of people across major media outlets into thinking that eating a chocolate bar every single day would cause them to lose weight.
It was everywhere.
People bought into it because it had the veneer of science.
And if we look at his methodology, how did he pull it off mathematically?
He tested 18 different variables. He didn't just measure weight. He continuously measured weight, cholesterol, sleep quality, blood pressure, sodium levels. He just kept throwing variables at the wall until the combination naturally forced the p-value below 0.05 for the weight loss metric.
Exactly.
But I want to clarify a really important distinction here. In the Bohannon study, or in the very real pharmaceutical trials we see doing this, they didn't actually falsify or invent any numbers, right?
No.
They didn't just type fake spreadsheet cells to make the chocolate look good.
That is the most insidious part of this whole phenomenon. No, they do not need to falsify a single piece of raw data. P-hacking relies entirely on fine-tuning the analysis to the data, rather than manipulating the data itself.
Right.
The numbers are real. It's the perspective that's forged. And in pharmaceutical research, this happens all the time.
Wait, really? How does this play out with actual drug companies?
Well, imagine a company spends millions developing a drug that turns out to have absolutely no discernible effect on its intended target. Instead of scrapping it, they run thousands of post-hoc analyses on their trial data.
Okay.
They drop certain patient groups, they select others, they adjust for age brackets, they change the primary outcome measures from cures the disease to slightly alters this one blood marker. Eventually, a strong, statistically meaningful effect magically appears.
And suddenly the press release says, new study shows this drug significantly improves memory function in women over 40.
Even though memory function in women over 40 wasn't even a variable they cared about or planned to measure when the trial started.
Wow. So the target gets painted around the arrow after it lands. You know, there's a great comparison in the sources between meteorology and epidemiology that really crystallized why some fields are immune to this and others are incredibly vulnerable.
Oh, yes.
Meteorologists, people predicting the weather, generally avoid data dredging. Why? Because their hypotheses are formulated using past weather data, and then they are forced to test those models against future weather.
Right. The future provides an unhackable proving ground.
Yeah.
You can't subconsciously hand-tailor your predictive model to fit the data because the upcoming weather hasn't happened.
Exactly.
You can't paint the target because the fence doesn't exist yet.
But then contrast that with an epidemiologist who is suddenly called into a town that has a terrifying cluster of cancer cases. They don't have a firm hypothesis for why it's happening yet, but they do have access to a massive historical database of demographic data for the town. Hundreds or thousands of different variables: diet, income, proximity to power lines, types of cars driven.
And most of those variables are totally uncorrelated to the cancer. But as we established earlier with the multiple comparisons problem, if you test enough of those variables against the cancer rate, the math dictates that at least one of them will correlate significantly, purely by accident.
Right.
A p-value of 0.01 just means 1% of the time that extreme of a result happens by pure chaotic chance. If you test thousands of independent variables in that town, you will get multiple significant hits that mean absolutely nothing.
So a few bad studies get published. It happens. But surely the broader scientific community corrects for this, right? Like, doesn't the sheer volume of research drown out the statistical noise?
Unfortunately, no, because this behavior creates a toxic ripple effect that biases the entire ecosystem of published science. When we look at the whole body of scientific literature, it's structurally skewed by systematic bias. Take the historical example of the HIV drug abacavir. Doctors realized that certain patients in their care were at a very high risk for cardiovascular issues. So, trying to be compassionate and helpful, they deliberately directed those high-risk patients to abacavir, and they put their healthier, lower-risk patients on different drugs.
Okay, so the doctors meant well. They were trying to protect vulnerable people.
They absolutely meant well. But years later, when analysts looked back at the raw hospital data to assess how safe abacavir was, the drug looked unfairly dangerous. It looked like it was causing heart attacks.
Oh, I see.
Why? Because the patients taking it were already prone to heart attacks before they took a single pill. The retrospective analysis didn't correct for this systematic bias. It's an unmeasured confounder, a hidden variable that completely skewed reality.
Man. And then there's the file drawer bias, which honestly might be one of the most depressing concepts in modern research.
Also known as publication bias.
Yeah.
This happens because the academic publishing industry heavily favors printing studies that have exciting, significant p-values.
Right.
If a researcher spends 2 years running a rigorous study and finds absolutely nothing, if the p-value is non-significant and boring, that study is simply left in a literal or digital file drawer and never published.
So if 20 different research teams around the world test a new supplement and 19 of them find out it does nothing, they all put their papers in a drawer.
Yep.
The one team that gets the 5% lucky statistical fluke gets published in a major journal, and suddenly the whole world thinks the supplement is a miracle cure. We literally only see the tip of the iceberg, and the tip is the anomaly.
That is the file drawer problem in a nutshell.
Yeah.
And the mathematical distortion gets even more complex when we look at multiple modeling.
Yeah.
Back in 1966, two statisticians named Selvin and Stewart came up with a brilliant analogy for this.
I love this part.
Yeah, when researchers are building complex explanatory models, they test dozens of variables and only keep the ones that seem to work, discarding the rest. Selvin and Stewart compared the retained variables to fish that don't fall through a net.
Right.
Because they were retained, their effects are mathematically bound to look much bigger than the variables that were discarded.
This analogy is so good. It's like inviting your friends over and bragging to them about the massive average size of the fish in your pond. But what you didn't tell them is that you intentionally bought a fishing net with huge holes, so all the small fish escaped back into the water before you even started counting.
Exactly.
You didn't miraculously discover a pond full of giant fish. You just purposefully threw away all the evidence of the small ones.
That is beautifully put. And the critical statistical insight from Selvin and Stewart is what this does to a metric called the mean square error.
Mean square error.
Mean square error is essentially a mathematical calculation of how far off your model's predictions are from reality, like how much natural variation or error there is in your data. Standard statistical formulas assume you are looking at an unfiltered, random, natural sample.
But the pond isn't natural anymore.
Exactly. Once you filter out all the small fish, your calculation of the pond's average error is artificially shrunk. You trick yourself into believing your predictive model is incredibly accurate and precise, when in reality you just cherry-pick the data to remove all the natural variation. The math literally breaks down if you apply standard formulas to a deeply filtered pond.
This all sounds incredibly bleak.
It can be.
Like, if the foundational math can be this easily manipulated, if our brains are wired to see patterns that aren't there, and if the publishing system actually incentivizes hiding the failures, how do we fix it? We can't just throw out the entire scientific method. How do we regain trust in the data?
Fortunately, the scientific community is acutely aware of this crisis, and there are incredibly powerful structural remedies being implemented right now.
Oh, good.
One of the most elegant methods is called split-half validation.
Okay, break that down for me.
It is remarkably simple.
Uh-huh.
You collect your massive data set. Then, before you do any analysis, before you even look at the numbers, you randomly partition the data into two completely separate, locked subsets, subset A and subset B.
Okay.
You are only allowed to look at subset A to explore the data, dredge the numbers, and create your hypothesis.
Oh, so you can do all the messy post hoc grouping and p-hacking you want over in subset A. You find your weird August 7th correlation.
Yes, have at it, but you
Re-
cannot publish yet. Once you've formulated that hypothesis from A, you must formally test it on subset B.
Oh.
Subset B was completely hidden from you while you were making your guess. If the hypothesis holds up in subset B, then it's highly likely it is a genuine discovery.
I love that. It forces you to paint the bullseye on fence B and then fire the arrow to see if it actually lands where you predicted.
Exactly.
But what about mathematical fixes? Can we just make the math harder to hack?
There are strict statistical corrections you can apply to your threshold. The most famous is the Bonferroni correction. Instead of using a lenient 0.05 significance level, you divide that alpha by the total number of tests you conducted. So if you ran 1,000 different significance tests looking for a correlation, you divide 0.05 by 1,000.
Wait, let me do that math. That yields a new threshold of 0.00005. Wait, isn't dividing by 1,000 almost too punishing?
It is very strict.
Like, if the threshold for success becomes that astronomically small, aren't we going to throw the baby out with the bathwater? We're going to miss out on actual, real, life-saving discoveries because the mathematical bar is impossibly high.
That is a highly debated point, and many statisticians agree with your hesitation. The Bonferroni correction is an extremely conservative, punishing metric. It brilliantly protects you from false positives, but it drastically increases the risk of false negatives.
Meaning you miss a real discovery.
Exactly. Because of this, modern researchers often use slightly less conservative, selective inference methods. The most common one is Benjaminian Hochberg's false discovery rate controlling procedure.
That's a mouthful.
It is, but it's basically a much more nuanced algorithm that controls for multiple tests without completely stifling scientific discovery.
But even with better math, it feels like the human incentives are still fundamentally wrong. Like, researchers still want that flashy result to get tenure, and journals still want that flashy headline to get readers.
Which is exactly why the most vital, permanent cure for the crisis is structural. It is a growing movement called open science, and specifically the shift toward a publishing model called registered reports.
Registered reports, how does that change the game?
So in a registered report, the authors write up a comprehensive study proposal. It includes their theoretical background, their exact research questions, their hypotheses, and precisely, step by step, how they plan to analyze the data.
Okay.
They submit this proposal to an academic journal before any data collection begins.
Wait, before they even look at a single spreadsheet?
Yes.
Huh.
The proposal is peer-reviewed right then and there, based solely on the merit of the idea and the rigor of the math. And if the journal accepts it, the paper resulting from the study is guaranteed to be published, regardless of what the study outcomes actually are.
Oh, wow. That destroys the file drawer bias completely.
It does.
If the result is totally boring and the p-value is completely non-significant, it still gets published for the world to see. It normalizes failure as a part of science.
Exactly. Journals like Nature, Human Behavior, and the European Journal of Personality are leading the charge on this front. As Nature Human Behavior puts it, this format shifts the entire academic emphasis away from the results of the research and puts it squarely onto the questions that guide the research and the methods used to answer them.
That is brilliant.
Science protects itself from data dredging by caring more about the integrity of the process than the sexiness of the outcome.
That is incredibly reassuring. It feels like taking the bucket of paint away from the archer before they even string their bow. You have to declare what a bullseye looks like before you shoot.
It completely restores the fundamental logic of the scientific method.
So we've gone from the basic math of p-values to the manipulative tricks of the data dredger's trade. Optional stopping, post hoc grouping, capitalizing on random August 7th birthdays.
Yeah.
We've seen how this leaks into the media with hoax chocolate studies and into pharmacies with manipulated drug analyses. And we've looked at the solutions, from split half validation to the brilliance of registered reports.
And if there's one overarching principle to take away from all of this, is the critical difference between exploratory analysis and confirmatory analysis.
Right.
Looking for patterns in data is entirely legitimate. It's how we generate new ideas.
Mm-hmm.
But that is exploratory. You cannot use the same data to be your confirmatory analysis. Statistical inference, the math of proving things, is only appropriate for the latter.
The next time you see a wild, highly specific scientific claim on the news, I want you to remember the data dredger's toolkit. Differentiating between exploring an idea and confirming a fact is the absolute key to being a well-informed consumer of information.
And I'll leave you with this final thought drawn from the sources. True statistical confidence is a joint property of both the data and the method used to examine it. You cannot look at a result in isolation.
And building on that, it really makes you wonder about the future. If artificial intelligence is now capable of running millions of data correlations per second, are we about to enter an era of automated p-hacking, like an era where algorithms generate thousands of spurious, perfectly hacked scientific discoveries a day?
It's a scary thought.
It all comes back to the wooden fence. A perfect bullseye means absolutely nothing if you don't know who painted the target and exactly when they decided to paint it. Thanks for taking this deep dive with us. Keep your eyes open, ask hard questions about the data, and we'll see you next time.